Utilizing a Bayesian point process statistical model to predict forest fires from charcoal data. Research conducted by Luke Onken and Aidan Draper, advised by Dr. Jason McLaughlin. Research funded by the National Science Foundation through the Computational Social Science Research Experience for Undergraduates program. Forest fires ravage the United States and the world every year. Just this past year, California and the West Coast experienced a devastating forest fire that forced many from their homes and also caused great air pollution. As humans, we can curb the effects of these forest fires if we knew how to predict when and where they would occur. In order to predict when and where they would occur, we need three things. First, we need vegetation data collected over the last few thousand years. This will tell us what fueled the forest fire. Second, we need climate data over the last few thousand years. This will show us what kinds of climates led to forest fires. And third, we need the actual data of when the forest fires occurred over the last couple thousand years. When we have all three of these components, we are able to form a forest fire simulation model. This simulation model could help policymakers and the general public be well informed, which could lead to better policies in the future and better public understanding. The last of those three previous components, having the knowledge of when forest fires occurred in the past, is not easy to come by. However, a postdoctoral researcher at Michigan State University, Dr. Malcolm Itter, has created a Bayesian point process statistical model that uses charcoal particles found in the bottom of lakes in order to predict when forest fires occurred in the past. The model distinguishes between two different kinds of forest fires. The first forest fire is the background intensity forest fire. This fire is within 20 kilometers of the lake. The second kind of fire is the foreground intensity forest fire. This fire occurs within 1 kilometer of the lake. In addition to distinguishing between background and foreground intensity forest fires, the model can also be run in two different ways. First, the model can be a univariate model, which only uses one lake as its source. However, the second way to use the model is a multivariate model, which uses many lakes in our region in order to better distinguish between regional and local fires. This summer, we took a look at Dr. Itter's model. No one has ever before looked at this model besides Dr. Itter himself, so we first took to validate the model. We took the code given to us by Dr. Itter and looked through it a little bit. We then ran the code with the data from the same lake that Dr. Itter used. We found that we got about similar results, which is good, as the model is a random model and should not always produce the exact same results, but similar results are always needed. Because we made this, we concluded the model was ready to try on a different lake in a different region of the country. We decided to use the model on Crystal Lake in Minnesota. After running the model, we had strikingly different results from the lake in Alaska. At Crystal Lake, the background intensity is much higher than that of Chopper Lake in Alaska. This can mean one of two things. First, it could mean that the regional fires in Minnesota are much higher than those in Alaska. However, the second option is that there could be many local fires in Minnesota around Crystal Lake that were attributed to the region, not the local. In order to distinguish between this, we need to run a multivariate model for all of the lakes in the surrounding region of Crystal Lake in Minnesota. A multivariate model will help distinguish between the background intensity and foreground intensity forest fires. After utilizing the model for lakes in Minnesota, we need to be able to use the model in different parts of the country more or less devastated by forest fires, including California. Getting knowledge in these places can help prevent further forest fires.